In this last half of Chapter 10, we're not going to be focusing on parametric equations anymore. We're going to shift to another type of equation and form of looking at graphs, and that's going to be polar coordinates and polar graphs. In this lesson, we'll focus on the details that could either serve as a review or an introduction to this idea of polar coordinates and polar graphs, and then in 10.4 we'll move to the calculus involved with polar graphs. So, how do we define points in the polar coordinate system? Well, before we talk about that, we should quickly review the regular Cartesian coordinate system, or as it's also referred to as the rectangular coordinates. Ultimately, these are just our xy points that we've been used to, and to define a point in the xy plane, we can start at the origin and move left or right depending on the x value of the point. After that, we can move up or down depending on the y value of the point, and then that gets us to the point that we're looking to plot. In the polar coordinate system, on the other hand, we have to look at things slightly different. In polar coordinates, points are identified by their distance r from the origin or the pole, hence the name polar form, and also by an angle theta from the horizontal right axis. So to get to a point in the polar coordinate system, we're going to measure out some angle from our zero angle, and then go out some distance r from the origin or the pole. That's how we're going to define points in this polar coordinate system. And this should remind you a lot of the unit circle. So, to practice plotting some of these points, we're going to have to keep some important things in mind. We're going to measure theta from the right side of the horizontal axis. Again, just like the unit circle, we'll start our angle measurements from there. If our angle is positive, we'll move counterclockwise, and if our angle is negative, we'll move clockwise. So just to practice plotting a few of these points, like we would have done, of course, when you first learned the xy points, let's go ahead and practice plotting the point 3, pi. And again, that's not x, y, that's an r, theta. Pi is our angle. So the first thing we need to do is plot, so to speak, that angle. In our xy plane, it didn't really matter if we started with x or y, but realistically with this polar coordinate system, we need to start with the angle and then worry about the distance r. So if we start at angle 0 and go pi radians in the counterclockwise direction, we'll end up on the left side of our horizontal axis. And then we can use this 3. Starting at the origin, we're going to go 3 units out in that direction. And of course, that places us at that point right there, so that's the point 3, pi. The next point we're going to practice plotting is 3, 3 pi. Again, we need to first plot or figure out where our angle is going to make us land. 3 pi would require us to go around 1 complete time, and then 1 more half to get to 3 pi. If we go around once, we'll be at 2 pi, and then another half over will of course get us 2 pi. From there, we count out 3 units from the origin, and that lands us back at the point we plotted previously. So we can plot this point that you see here in red 2 different ways. Next, we're going to plot the point 3, negative pi over 2. Since it's a negative angle, we need to go in a clockwise direction, pi over 2 radians, and then out from the origin again, or the pole, we'll count out 3 units and put a dot at that point, and that's the point 3, negative pi over 2. One more point to plot will be the point negative 3, 2 pi. Again, we need to start with the angle, so 2 pi would be 1 revolution around back to where we started. But here's where we have to be careful. Negative values for r require us to go in the opposite direction. If this was a positive 3, we would be putting our dot right here. But since it's a negative 3, we need to go in the reverse direction and plot that point. And again, we've landed back at the point we plotted in the previous 2 practice points. I guess bottom line is what we're trying to get at here is that the points negative 3, 2 pi, 3, pi, and 3, 3 pi are really all the same point. So there are many ways many different ways of expressing the same point, which is kind of something you came to appreciate, I think, from plotting, or not plotting points, but graphing the unit circle and talking about the points as you go around the unit circle. So those are the basics of plotting points in our polar coordinate system. It won't really affect us too much in terms of these problems we're going to be looking at, but it certainly will help guide us in trying to understand this new way of looking at points. The next thing we need to do is address the basic graphs in the polar form. You know, it's nice to graph points, but of course when we studied our xy plane, we quickly went from points to graphing functions. And that's kind of the same idea here. We're going to focus on graphing polar graphs and not so much just the points themselves. So we're going to take a look at two basic graphs. And just as a quick analogy to our xy graphs, if I asked you to graph x equals 2, you would of course graph a vertical line at the x value of 2. If I asked you to graph y equals 2, we would graph a horizontal line at y equals 2. So those are the two very most basic graphs in our xy plane. So what would kind of be the analogy in the polar world? Well, if we were to graph r equals 2, that would be all the points whose distance from the origin is 2. And of course, all the points whose distance from the origin is 2 would be just a circle of radius 2. So in polar coordinates, the equation r equals some number results in a circle centered at the pole with a radius of that number. What if theta is just equal to a number? Well, if theta is just equal to a number like pi over 3, that would be all the points with angles of pi over 3. That would look like a straight line at an angle of pi over 3. So in polar coordinates, the equation of theta equals a number results in a line through the origin at the angle that you're looking at. So once we get used to plotting points in our polar coordinate system, it can be helpful to convert between polar and rectangular coordinates. So here we have a point graphed in our xy plane, so we went over some value x, we went up some value y, and that gets us to this red dot you see there. But let's say I wanted to define that same point using the polar form. Well, we would have to go some angle theta up from our 0 angle, and then out some distance r from our pole to get to that same point. And how do we convert between these two forms when we're talking about the same point? Well, we're going to use a little trigonometry to help us out here. To convert from polar to Cartesian, or the rectangular coordinates, we need the relationship that's given by this right triangle that you see right here. If we look at cosine theta, if we look at that trig ratio would be x over r. And if I wanted to figure out what x was equal to, I would just of course multiply the r to the other side. So if we want to convert polar to rectangular coordinates, we would take the r and multiply by cosine theta, and that would give us our x component, or our x value of the point. The sine trig ratio ties the y to the r. If we wanted to find the y component of our point, we would of course just need to multiply the r to the other side, and the y value would be equal to r sine theta. So that's if I give you polar form and I want you to change it to rectangular. If you want to go in the opposite direction and go from xy to polar, there we're just going to use the Pythagorean theorem. We know that x squared plus y squared equals r squared. And if you want to find r, if I gave you an x and a y value, you would just need to square those two values, add them, and then take the square root. To find the corresponding theta, we would have to rely on our last trig function we haven't addressed, and that's the tangent trig ratio. Tangent of theta would be y over x. So if I gave you an x and a y value, and I wanted you to find what theta was, you would just have to take the arctan of that fraction, y over x. So to practice converting back and forth, we're going to take this polar point 2, pi over 4 and change it to its rectangular coordinates. So I'm going to just plot it here real quick just to get a visual, and what we're trying to do is find the x and the y value of this point in red right here, which is the polar point 2, pi over 4. All we need to do is take our two formulas above and plug in the values that are appropriate. Our r is 2, our theta is pi over 4, so when we plug that into the x and the y equation, we'll get square root of 2 for the x and the y value. And then once we realize that, we can say that our rectangular point is square root of 2 comma square root of 2. So a very easy thing to do if you need to go back and forth between polar or the rectangular coordinates. What if we start off with an xy value and I want to find the polar point that corresponds to that? Again, just as a visual, I'm going to plot the point 1, 2, but ultimately we're just going to use the formulas from above to help us find that polar point that corresponds to 1, 2. R would be the square root of x squared plus y squared, and of course when we plug those values in, we'll end up with the square root of 5, and we're going to leave that exact and not round that off to a decimal. To find theta, we need to take the y over the x value and find the arctan of that. Here, the value would be arctan of 2 if we're going to leave it exact. If you need a little more easy number to look at possibly other than arctan 2, that would be equivalent if you typed it into a calculator to 1.107 radians. So ultimately, if we wanted to write this point 1, 2 in polar form, we would have to write a radius of square root of 5 and an angle of arctan of 2. Okay, so what we really need to focus on now in preparation for 10.4 is looking at polar graphs. You saw the two basic ones in the first slide of this section, but now we need to really focus on graphing polar functions. So just to kind of bring you up to speed for what we're really trying to do here, of course if I asked you to graph y equals x, that's not a big deal, that's just our linear parent function. If I asked you to graph y equals x squared, again, not a big deal, that's just a parabola. So you know all the parent functions for our rectangular coordinate system. That's what we're trying to accomplish here with this lesson. The more familiar you become with these polar graphs, the better off you'll be in understanding the calculus of what's to come in 10.4. So really look at these next couple slides as just giving you all the information of these graphs that you're going to need so we can take that to doing the calculus with these graphs in 10.4. So what if you were asked to graph r equals theta? Kind of the analogy of saying y equals x, which is our linear function. Well, what that would produce is a graph where the change in the radius corresponds to the exact same change in the angle, since they're both equal to each other, kind of like y equals x. What happens when we do that is for every theta, it's the exact same r. And when you plot those points, you end up with a spiral. So kind of add this to the list again of all these polar graphs that you're going to need to become familiar with. And luckily, graphing these graphs is very similar to doing it in the xy plane. 0, 0 would be this point right here. Pi over 2 comma pi over 2 would be this point right here. Pi comma pi would be this point. 3 pi over 2 comma 3 pi over 2 would be this point. And then 2 pi comma 2 pi would be this point. It's going to be very important that you understand how to trace out these graphs. Because if I asked you to graph this graph just from 0 to pi over 2, you would need to know that we're really just talking about this little piece right here that I'm shading in. And in 10.4, that will become very important. If I asked you to graph this graph from 0 to, let's say, 0 to pi, that graph would be all of this part shaded in. Ultimately, what I'm going to kind of jump ahead to is talking about for 10.4 that we're going to be finding the area of these polar graphs. So you need to know how much of the graph is drawn depending on what the particular window or interval happens to be. Just again as one more example, if I asked you to graph 0 to 3 pi over 2, we would be talking about all this area right here. And again, just kind of getting you ready for 10.4, what if you were asked to find that area? Well, you would need to know up to what point, so it would be 0 to 3 pi over 2, that we would be concerned with. So kind of get some practice with that, and then again, 10.4 should be a lot easier to understand. The next graphs we need to become familiarized with are the circles in the polar coordinate system. When r equals sine theta, and here are some points here to help you see it visually, you'll end up with a circle. Again, looking at these points is going to be very important. 0, 0 is right here. Pi over 4, square root of 2 over 2 is right here. Pi over 2, 1 is right here. And then, to kind of round it out, pi, 0 lands us back at this point to make this complete circle. And again, it's very important to see if you were asked to just graph this from 0, let's say, to pi over 2, you of course would be graphing this right side of the circle. So again, very important that you see how these points are plotted so that you can see how much of the polar graph you're looking at in certain situations. So to kind of generalize this more so you can have the pattern for these circles, if you ever have an equation where r is equal to a number times sine theta, you're going to have a circle. The center of that circle is going to be at 0, a over 2. The radius of that circle is going to be a over 2. And you can kind of see this pattern down here of all the circles I graphed. When a is equal to 1, it's this very small circle. When a is equal to 2, the next one bigger, and so on and so forth. One giant key that you're really going to want to highlight and make note of is this. These circles are generated as theta goes from 0 to pi, as you can see over here in the table that we made. As soon as you pass pi, you're going to be tracing over the circle that you already drew. And that's going to be very important again as we're looking at area in 10.4. The last kind of circle you'll run into is when r is equal to cosine theta. Same kind of concept applies here, except things are a little bit switched in our information. The center is now at a over 2, 0, and luckily the radius is still a over 2. Again, very, very important to realize these circles are going to be generated as theta goes from 0 to pi. As soon as you pass pi, you're going to be tracing over the same circle that's already been drawn, just like the unit circle. But in this case, not 0 to 2 pi like the unit circle, 0 to pi. So again, please make note of these things as it's going to affect your success in 10.4. Okay, one last slide of these very interesting polar functions and definitely some really interesting graphs here. First, we're going to talk about Rose curves. They have a general form where you're going to see an r equal to a number times cosine times some number theta. They could also appear as r equals a number sine a number times theta. So let's take a look at our first case here. In general, if n is an odd number, the number in front of pi, if that number is an odd number, the Rose curve is going to have n equally spaced petals. And you can see here, if we graph r equals cosine 5 theta, we see 1, 2, 3, 4, 5 petals, and they're all equally spaced. The length of each of these petals is the number in front of your cosine here. And you can see there's of course an invisible 1 here, so the length of our petal is 1. These graphs, again, just like the circles in the slide before, are generated as theta goes from 0 to pi. A very important idea. Again, try to get practice understanding this, because once you pass pi, you're going to be tracing over the Rose curve that you've already drawn. And that may or may not be appropriate when we're doing problems in 10.4. If we have n being an even number, like we see here with cosine 4 theta, we're actually going to double the amount of petals. In other words, we'll have 2 times n equally spaced petals. So of course, if n is equal to 4, that should mean we have 1, 2, 3, 4, 5, 6, 7, 8 petals. And again, they're all equally spaced. Here's where things get interesting and is kind of easy to confuse in terms of this being a fairly new topic for everybody. Things get changed a little bit here because when n is even, this Rose curve is generated when theta goes from 0 to 2 pi. So if you were to say only graph 0 to pi for one of these even petal rose curves, you'd actually only end up with half of it. And I'll talk about that in the next slide with the TI-89. But again, it's a easy thing to kind of forget that when we're odd, this rose curve is generated from 0 to pi. When it's an even amount, it's generated from 0 to 2 pi. And again, if we pass 2 pi in that case, we would be tracing over the petals that already exist. And then kind of just to wrap up the information you need for these rose curves, for cosine, there's going to be one petal centered at theta equals 0, like you can see right here in these two examples. For sine, on the other hand, and we'll take a look at one of these graphs a bit later, sine starts at pi over 2n. So it's going to be somewhere over here in the first quadrant for the first petal, depending on how many petals there are. So those are our rose curves. Common, but I would say maybe a little more common in a sense concerning the AP test might be these graphs called cardioids. They have the form r equals a plus, and I guess we could use some parentheses here possibly. It's going to be a plus a number times cosine theta. And a and b are the same number, and those of course are constants. The graphs of cardioids are generated as theta goes from 0 to 2 pi. Its graph, just in a general way of looking at it, looks like a circle, but it's kind of been pushed in a little bit with a dimple. Again, it's going to be very important that you understand how these graphs are traced out. From 0 to pi, let's say, or from 0 to pi over 2, it's only going to trace out a certain part of this graph. So again, maybe if all we wanted to do was find this area that I'm shading in right here, we would have to know from what angle to what angle that part gets traced out, or any other piece of this graph. Another graph we're going to have to be very familiar with is something called a limason. Here it's got the same equation as a cardioid, but now the A number is less than the B number. Luckily, the same idea still applies in terms of how we graph it. As long as theta goes from 0 to 2 pi, we've drawn one limason. If we pass 2 pi, then we're tracing over the already drawn graph. This graph kind of looks like a cardioid, but that little part that was being dimpled or pushed in kind of got pushed in even more, and it created a loop on the inside. Again, it's going to be very important that you understand how much of the graph is traced out, say from 0 to pi, or maybe 0 to pi over 2. Because what'll end up happening in 10.4 is we might only want to find the area of this part of the inner loop. Or possibly we might want to find this part of the limason in terms of area. So again, becoming familiar with these graphs is going to be vital for 10.4. The last graph we need to possibly be concerned with is something called a lemniscate. That form looks like r squared equals a squared sine of 2 theta, and again, a is just a constant. These graphs are generated as theta goes from 0 to 2 pi, and of course, it looks like this figure 8 graph. If you've ever been curious about how you might want to graph a infinity symbol, that's a lemniscate. But in this case, it would be r squared equals a squared cosine 2 theta. Okay, so you've heard me say through several of these slides, it's going to be vital for you to understand how much of a polar graph is graphed depending on how big theta is. So if theta goes from 0 to pi, let's say, how much of the polar graph is going to be graphed? If theta maybe goes from 0 to pi over 2, how much of the graph is going to be graphed in that case? Or maybe theta goes from 0 to 2 pi. No matter what the case is, your success for 10.4 is going to rely heavily in understanding how much of a polar graph is graphed, depending on how big theta is. To help you achieve that knowledge, playing with your TI-89 is going to be very helpful so you can see how much of these polar graphs are graphed, depending on how big theta is. So definitely at the end of this slide, you might want to pause and go through this, or maybe pause as I'm going through these animations, but ultimately definitely invest in this time right now, because ultimately your success in 10.4 will be heavily dependent on your ability to see these graphs depending on how big theta is. So the first thing we have to do in the TI-89 is make sure we're in radian mode. We never deal with degrees, so please make sure it's in radian mode. The next thing we need to do is change our graph mode to polar. So let's say I wanted to graph the polar function 5 sine 4 theta, and you do have to use the theta button when you're using the polar mode. Here you might recognize that as a rose curve from the previous slide, where n is an even number, and in this case it's 4. We're going to have to again recall that these rose petals, especially when n is an even number, are generated as theta goes from 0 to 2 pi. And kind of like I was saying in the last slide, of course if theta only went from 0 to pi, we'd only get half of our graph. Or if we made theta go from 0 to an angle bigger than 2 pi, we'd be tracing over the graph of the rose curve that's already been made. So what we need to do is go into the window here and adjust some stuff. Our theta, as you can see right here, needs to be adjusted. We only want to graph this rose curve once. We don't want to trace over it again, and we don't want to necessarily graph half of it. So we need to change theta max to 2 pi so that we can get this one rose curve complete. If you go to the graph, you'll see the graph. And again, kind of recall that if n is an even number, that means we're going to have double the amount of petals of n. And you can see here that there are 8 of them. On top of that, I didn't get a chance to show one of these rose curves in the last slide concerning a sine rose curve, but the first petal is not centered on x equals 0, or the x-axis. The first rose curve is in the, or the first petal, sorry, of the rose curve is in the first quadrant. So let's say you did end up graphing from 0 to pi. If you go in and change theta max to pi, you can see that it graphs half, or the 4 petals that you see here. So again, understanding how much of a graph is graphed is going to be absolutely vital in terms of 10.4. Sometimes these graphs don't quite look as nice as they can because it's a little stretched in terms of the way the x and the y are set up. So if you want a nicer, maybe I should say, looking graph, if you go to zoom and zoom square SQR, which is choice 5, you'll get a nicer looking graph that's not stretched in one direction or another. One other thing to watch out for when you're graphing these polar functions is concerning this theta step that you see right here under theta min and theta max. Theta step is just best left at 0.05. And that'll give you the nice smooth looking graphs that you would want to see. The graph will end up being boxy if that theta step value is too big, so it's best just to keep it at just in a general sense of a value at 0.05, and then you shouldn't run into any issues. So again, please practice these things because your, again, success in 10.4 might be totally dependent on you understanding how much of a graph is drawn, depending on how big theta is. Okay, the last topic we need to go over before we get to 10.4 involving the calculus involving these polar functions is what if you're given an equation in rectangular form and you want to change it to polar form. Well, luckily it's a lot like, in a sense, when we change the points from rectangular to polar. We're going to use those equations from a few slides ago to help us out. The other thing we're going to do is try to sketch the graph. So if you recall from a few slides ago, we know that x is r cosine theta, which will all be squared because x is being squared. Y is r sine theta, and then we need to subtract 2 and then square all that, and that's equal to 4. Probably not the best form to leave that in, so we can try to simplify this. And really the only thing we can do to simplify is to square each of these terms. In this first term, we're just going to, of course, end up with r squared times cosine squared. But in this term, be very careful you don't fall for the typical mistake here. We're not going to write r squared sine squared minus 4. We need to use the process of distribution or FOIL or maybe a box method to multiply a binomial, which are these two terms, which makes it a binomial. When you have a binomial squared, we have to multiply that out with some sort of distribution process or maybe FOIL or the box method. So there's the result. There's a few things we can do here. On the left and the right side, we have a 4. So if we were to subtract that 4 to the other side, of course we'd end up with 0. The other thing we can do, if you notice these two terms right here both have an r squared in common, we can of course factor out that r squared from both terms, and then we'll be left with cosine squared plus sine squared. Of course, the minus 4r sine theta just stays as we can't alter it at all. There's some good news here. If you recognize cosine squared plus sine squared to be a Pythagorean identity, that is great, because that is all equal to 1. So ultimately we're left with r squared minus 4 sine theta, and for the sake of space here, because I'm running out of space for the steps, I'm going to go ahead and do 2 steps in one here. I'm going to call cosine squared plus sine squared 1, and then also recognize that this term, which is r squared, and this term, which is negative 4r sine, both have an r in common. So I'm going to factor out that 4. After that, just like our regular xy equations, when you have two things being multiplied equal to 0, we can set both of those equal to 0. R being equal to 0 is pretty much nothing. If r was equal to 1, that would be a circle. If r was equal to 2, that would be a circle. But if r is equal to 0, that's, I suppose, just a point, and it's not much of anything in terms of a graph. So we can pretty much disregard that. If we take that 4 sine theta and add it to the other side, we'll end up with r equals 4 sine theta. And if you're somewhat familiar with these polar graphs, you might be recognizing that as the equation of a circle. A circle with a center at 0, 2, it's going to be 0, a over 2, if you want to recall from a few slides ago, and our a here is 4, so 4 over 2 is 2. And then of course the radius we're dealing with here is also 2. Here we're going to go in the other direction. What if we want to convert this polar equation to rectangular form and then graph it? Well, what we can do here as a means to an end is to multiply r by both sides. You might not have realized to do that without seeing an example like this, but after you see the result of that, it might become more apparent why we're multiplying r on both sides. We're going to end up with r squared on the left side, and then 3r sine theta on the right side. And I put the r sine theta in parentheses to emphasize that r sine theta is just equal to y. So we're left with 3y on the right side. R squared is x squared plus y squared. And from here we can do some algebra 2 skills. What I'm going to do is subtract that 3y to the other side. And these problems should remind you of the conic section problems you've done in your Algebra 2 and pre-calc classes in the past, because what we need to do here is complete the square for this y squared piece. X squared is all on its own because there's no other components to it, so there's no completing of the square we can do here. But if you recall the process of seeing equations like this in prior math classes, we would need to complete the square for the y squared minus 3y. So as a reminder, because we saw this before way back in chapter 5, to complete the square, we take this number b and divide it by 2. So it'll be negative 3 divided by 2, and then we square that number, which is of course just equal to 9 over 4. I'm going to add 9 over 4 to this set of y terms, but of course, if I do that on the left side, I'd also have to do that on the right side to balance that out. The reason we do that is so that we can now factor this. The whole point of completing the square is to achieve a trinomial that is factorable. To factor that, we're just going to end up with pretty much what was in our b over 2 case. The negative 3 over 2 squared actually ends up being the factor that you're dealing with. So of course x squared just remains x squared. Our trinomial here will end up being factored down to y minus 3 halves all squared, and that's equal to 9/4. If you again are up to speed with your conic sections here, you'll recognize this as the equation of a circle. And the equation of the circle that we're dealing with here, it has a center of 0, 3 over 2. If you recall, this x piece is really x minus 0 squared. And our center of our circle is always the h, k, if you recall that notation from conic sections. So our center for this circle would be 0, 3 over 2. And of course, by virtue of that, the radius is going to be 3 over 2. We would have to take the square root of this, which is our r squared, and that would just give us the radius of 3 over 2.